Hello, and today we are going through the Combined Science Chemistry Paper 2 Higher from June 2019. There'll be a sort of a two-part video. I will be covering the first half of the paper and Mr. Deighton will be covering the second half. So do not be alarmed at the change in voice halfway through. So let us make a start. So our first question is about water. So water that is safe to drink contains dissolved substances. What do we call water that is safe to drink? Well, water that we can drink is called potable water. So I will tick potable. Describe a test for pure water. Give the result of the test if the water is pure. So the test that we do to find out if something is pure is to boil it and to check that its boiling point is at the correct temperature. So our test is to boil the water, and if it is pure, it will boil at exactly 100 degrees Celsius. It will boil at 100 degrees C. That's all we need for that. Question 1.3. Describe a method to determine the mass of dissolved solids in a 100 centimeters cubed sample of river water. So we are describing a method. So we need the steps in the method and think about how we would do this as a practical. So if we are looking at 100 centimeters cubed of water, and we want to know the mass of what's dissolved in it. So if we're looking for something that's dissolved, it means we need to get rid of the water. We need to evaporate it off to leave our solids behind. Okay, so you would have done this many times. First thing we need to do is we need to think about what we're going to put our water in to boil it. We don't really want to have lots of moving around of our solids. We want to try and keep it in the same container the whole time. So I know that I'm going to need an evaporating basin because I have to get rid of my water. So I'm going to do my whole experiment in an evaporating basin. So first thing I should do is weigh my evaporating basin. Okay, weigh your evaporating basin. Next thing, I need to put my water in. So measure my volume of water, or put all of the water into the basin. Now, the reason I say measure the volume is that 100 centimeters cubed might not fit. So you might only put 50 in, or you might only put 10 in, but you need to make a note of how much you have put in to start with. And then once you're there, then you can start evaporating. So heat to allow water to evaporate. You've got to keep going until it is dry. So when dry, you need to weigh the evaporating basin. So that will obviously give you the mass of the solids and the basin, and hopefully you can see now why we weighed it in the first place, because what are we going to do? We're going to subtract the mass of evaporating basin to give mass of solids on their own. Now, it might be worth mentioning here, if we only used 50 centimeters cubed or 10 centimeters cubed, then obviously your mass of solids need to be multiplied depending on what you used. Use mass to determine mass from 100 centimeters cubed. So e.g. if using 10 centimeters cubed, then you'll need to multiply by 10. If using 50 centimeters cubed, you need to multiply by 2. because obviously the question's asking the mass from 100 centimetres cubed. Okay, to keep things simple, you could just say use 100 centimetres cubed and that will have your overall mass. Okay, so the key things here is you have to know how much water you are using. You have to heat it until it is dry, because you need to make sure there is no water left, and then determining the mass of the solid in order to make sure you're doing it out of 100. 1.4, a sample of river water contains 125 milligrams per decimeters cubed of dissolved solids. Calculate the mass of dissolved solids in grams in 250 centimeters cubed of this sample of river water. Give your answer to 2 significant figures. Right, lots of information there. So we've got 125 milligrams per decimeters cubed of dissolved solids. Calculate the mass of dissolved solids in grams from 250 centimeters cubed. And then we've got 2 significant figures. So the key thing here that should be screaming out at you is that we have got lots of different units. Okay, things aren't all in the same units here, so we're going to have to do some conversions. Okay, I would say you need to convert to grams because that is what the answer wants it in. And I would convert to decimeters cubed. Okay, so first thing first, 250 centimeters cubed to dm cubed, you need to divide by 1,000. 250 divided by 1,000 is 0.25 decimeters cubed. Okay, centimeters to decimeters is divide by 1,000 because a decimeter is bigger than a centimeter. So we've got 0.25 decimeters cubed. I next need to convert my milligrams into grams. So 125 milligrams to grams. Again, a gram is bigger than a milligram, so I need to divide here. So 125 divided by 1,000. .125 grams. Okay, so my sample of river water contains 0.125 grams per decimeters cubed. Calculate the mass of dissolved solids in 250 centimeters, or 0.25 decimeters cubed. Okay, so if I want to know, so per 1 decimeter there's 0.125 grams. Per 0.25 decimeters, I'm just going to have to times them together. So 0.25 times by 0.125 will give me 0.03125. 2 significant figures. So I need to change that to 2 significant figures. So I've got 0.031 grams. And that is my overall answer. So conversion, multiply them together because you're doing how many per that much, and then 2 significant figures, 4 marks. Question 1.5. Another maths question. A water company allows a maximum of 500 milligrams per decimeters cubed of sulfate ions in drinking water. A sample contained 44 milligrams per decimeters cubed of sulfate ions. Calculate the percentage of the maximum allowed mass of sulfate ions in the sample of drinking water. Excellent, a lovely easy percentage question. We don't have to do any conversions because they're both in the same units. So all I'm doing is what is 44 as a percentage of 500. And as you should all know, super easy, 44 out of 500 times 100 will give you your percentage. 44 as a percentage of 500 times 100 to turn it into a percent, and that gives you 8.8%. Nice, easy 2-mark question there. Question 2. This question is about atmospheric pollutants from fuels. Fuel burns in a car engine. Describe how oxides of nitrogen are produced in a car engine. So how do we get nitrous oxides being produced? Okay, so in order to get nitrous oxides, you need to have nitrogen and you need to have oxygen, and they need to be able to react together. And what is going to help them reacting together is very high temperatures. It needs a lot of energy. So we need a high temperature from the engine, basically. And that causes our oxygen and nitrogen to react. And they bond together. And that's it. Okay, high temperature is needed. We need oxygen and nitrogen to react, bond together. Okay, question 2.2. We have a 6-mark question here. Table 1 shows the carbon footprint during the manufacture and use of 3 cars. This is all our information. We need to evaluate the carbon footprint of the cars. Okay, so evaluate is good things, bad things, and overall judgment. Now you've got a lot of information here, so I would take time before you start writing to just figure out what all this information is. So we've got 3 cars. It's telling us the mass of carbon dioxide produced whilst it was being made. The mass produced when driving in kilograms per kilometre. So every kilometre, that's the kilograms of CO2 being produced. And then these two are quite similar, but do give us quite interesting numbers. So this is, if you add together manufacture and driving 40,000 kilometres, that's what you'll get. And if you add together manufacture and driving 100,000 kilometres, that is what you'd get. Okay, so let's have a look at each one now individually. So the mass of CO2, we're evaluating. So we just want to know which one's the best, which one's the worst. So just write that in. Car A has the least, so that's the best one. And car C has the most. Okay, so during manufacture, car A is better than the other two, car C is the worst. Mass of CO2 produced when driving in kilograms per kilometre. So actually car A here is my most, and car C is my least. Okay, so this is quite interesting. So that's the opposite from manufacturer to actually driving it. So how does that then affect manufacturer plus driving in these 2 other columns? So we can see that when you add together manufacturing and 40,000 kilometres of driving, car A has the least, car C has the most, but there's not that much in it. Okay, it's quite close to car B. So I'm just going to put close to that one. And then after driving 100,000 kilometres, car A is still the least, but now car B is the most. And actually car A is kind of catching up with car C. So it's only just the second one. So with all this information, we can now start doing our evaluation, okay? So we're evaluating the carbon footprint, and we've got lots of information here. So let's just go straight in. In manufacturing, car C produces the most, and car A produces the least. We'll start with that. So in manufacturing, car A produces the least, and car C produces the most. Okay, nice. Driving per kilogram per kilometre, car C produces the least, and car A produces the most. Okay, so that's quite clearly what we've figured out from that bit. And then we can keep going. Let's say after 40,000 kilometers, including manufacture, car A produces the least and car C produces the most. Okay, so that's that box. And then lastly, after 100,000 kilometers, including manufacture, car A produces the least and car B produces the most. Okay, so all I've done here is looked at my information and sort of re-said that. At the moment, we're only really looking at a level 1 to 2 answer, okay, because I've not put a judgment yet. That's going to come at the end, and I've not started really linking things together. I've just I've shown that I can understand the table. So at the moment, we're probably, 2 to 3 marks. So let's start actually analysing what we've got in the table. So what I can see is that car A produces the least in manufacture, but the most in driving per kilometre. Okay, so that's kind of making a link between them. We're not looking at these as separate things, but we're saying, well, that's the least there, but the most there. So we've actually shown that. We can do the same for car C. So car C produces the most in manufacture. So that was a key thing, but least in driving. Okay. So then we kind of need to start making our own judgment. Now, to start with, you may think, well, actually, car A is the best. So car A is the best because generally it's the least all round. Yeah. But if you keep looking, eventually car A is going to be the best. Sorry, car C is going to be the best, because over just 100,000 kilometers, it's already moved to less than car B. So it's not going to take that much more for it to then end up being less than car A, because you can see that the gaps between them are getting smaller and smaller. Eventually, car A will overtake the other two because it's got the most for driving. So the more you drive it, the worse car A gets. Whereas the more you drive car C, the better it will do comparatively to the other two. So that is where your judgment comes in about which one is best. You've realised that actually once you're using the car, this becomes the most important part, because that's just a fixed cost at the beginning, but this is what's going to actually change throughout the life of the car. So you could say eventually car A will have the largest carbon footprint as cost of driving. Sorry, that should be mass of driving is the highest, whereas car C will eventually be the smallest carbon footprint as mass in driving is the least. Okay, so I have clearly explained what my table is showing me. I've compared the cars and I've compared their mass of CO2 in manufacturing and driving, and then I've given my own judgment at the end. Okay. So question 3. This question is about chromatography of food colouring. Food colouring is a formulation. What is a formulation? This definition should be ingrained into your brain. A mixture designed as a useful product. Okay, mixture, designed, useful. They're the 3 things that we need. Explain how paper chromatography separates the dyes in food colouring. Do not give details of how to do the experiment. So they don't want to know how it's done. They just want to know why it works, basically. So how does it separate the dyes? So we know that the whole thing for chromatography is about solubility. So the dyes have different solubilities. So they move up the paper at different rates or different distances. Okay, so they're different solubilities. You could talk about the attraction between the mobile phase and the stationary phase. That would be a really good thing to get in here as well. So mobile and stationary phases, if you want to talk about them, that would also get the mark. And if you couldn't remember that word, for example, solubilities, you could say they attract differently to the mobile and stationary phase, so that would be fine for the first mark. And then moving up the paper at different speeds or different distances. Okay, not time, it's not how long it takes, it's how quickly it moves. 3.3, explain how the student could tell from the chromatogram that the food colouring contained more than one dye. It's 2 marks this, so we've got to say 2 things. Okay, we know 2 things that would lead to having more than one dye. So we know that we would have different dots or different colours, or you could say more than one dot. But you've got to then specify that as in one line. Okay, so different dots or more than one dot in a vertical line or in a vertical column. Okay, so that's really clear. So you've really clearly said that it's in the vertical, because if you're doing more than one colour, you're going to get more than one dot, but it's more than one dot in a vertical line means it's come from the same original substance. So just make that really clear. Assume the examiner's a bit silly, doesn't understand. Okay, question 3.4. Explain how the student could use chromatography to identify unknown dyes in the food colouring. So we've done the chromatogram and we've got our dots. How could we then identify those unknowns? How could we find out what they are? So if you need to identify something, then you need to have things to compare it with, things that you do know. So you need to run known dyes or colours. You need to compare, remember that key word, we need to have a comparison. So compare the distances. What else could you compare? You could compare the RF values. Okay, both of them are valid comparisons to knowing whether they are the same or not. So then you just need to take that one step further. So if we've run our known dyes and we've looked at the distances and the RF values, what can that then tell us? So if the distances are the same, or the RF values are the same, then it is the same dye or the same colour. So anything that's the same means it's the same colour. And now I'm going to move over to Mr. Deighton.
Okay, so you might have realised there's been a change of voice. That is because I'm doing the second half of this paper, starting from question number 4. So question 4, this question is about copper and fuels. Copper is extracted from low-grade ores by phytomining. Describe how copper metal is produced by phytomining, and it's worth 4 marks. So we must make sure we've got 4 points that they can give us marks for. So phytomining is in the higher section only, so it's very likely that it will come up. If we're using plants, which is what phytomining is, using plants to get the copper, the first thing we need to do is grow our plants. So growing plants on the ore, or the low-grade ore, either way. And then once we've grown the plants, we then need to get the plants and we burn them. So that would be your second mark. So 1 mark about growing the plants on the ore. The second mark is going to be about burning them. So then we need to make, after we burn them, make a copper solution, a copper compound solution. So we normally do that by dissolving it in acid, and that gives us a solution of copper compound. So if you've said dissolve it in sulfuric acid and you'll get copper sulfate, something like that will be absolutely fine. So that's going to be our third mark. So then the fourth mark is how we get pure copper from that compound, and there's 2 ways in which you can do that. So if you have mentioned the word electrolysis, then that will get you a mark. The alternative to get it from electrolysis is, sorry about that, a fire drill just went there. So apart from electrolysis, the other way in which you can get pure copper is to use a displacement reaction. So you can either mention displacement reaction or electrolysis for the 4th mark. Okay, question 4.2. Another method of extracting copper from low-grade ores is bioleaching. So we need to know about phytomining and bioleaching. A solution of copper sulfate, CuSO4, produced by bioleaching has a concentration of 0.319 grams per decimeter cubed. Gives you the relative atomic masses of copper and oxygen and sulfur. Calculate the number of moles of copper that can be produced from 1 decimeter cubed of solution. Now this is worth 3 marks, so it's a little bit more complicated than usual. The first thing you need to do is work out the molecular mass from the atomic masses. So to do that, we need to add them all together. So you've got 1 copper, you've got 1 sulfur, and you've got 4 oxygens. Now if you pop all of that into your calculator, you should get a number of 159.5. Okay, so the MR is 159.5. So if you have got 159.5, that actually gets you 1 mark. Now this is for 1 decimeter cubed, so we can get rid of that and we can call it 0.319 grams. So to work out the number of moles, it's the mass divided by the molecular mass. Okay, so the mass, as we said, is 0.319, and we're going to divide that by the molecular mass, which is 159.5. and if you've got that, then that is worth a mark. Now that, if you pop that into your calculator, will give you 0.002 moles. You might have put 2 times 10 to the minus 3, that's absolutely fine. That is your third mark. If you've got that, then that automatically is worth 3 marks, okay? But always show you're working out. Next part, copper is used as a catalyst. So figure 1 shows reaction profiles for a reaction with and without a catalyst. 4.3, how do the reaction profiles show that using a catalyst does not affect the overall change for the reaction in terms of energy? Now on this, say you want to go through each of these statements and decide if they're true or not. Remember, you can write on the side, you're not going to get marked down. So both reaction profiles show exothermic reactions. Now that's actually correct, because both of them go lower than the starting, which means they've given off more energy than what they took in. But that doesn't show us that the overall that there hasn't been an overall energy change for the reaction. So it's not going to be that one. Both reaction profiles start at the same energy level, and at the end they're also at the same energy level. So does that show us that using a catalyst does not affect the overall energy change? It does. We'll keep going though, just so that we can make sure that we're right. So both reaction profiles show the activation energy. That is technically correct, but that doesn't tell us that the catalyst doesn't affect the overall energy change. So it's not going to be that one. And the activation energy for the uncatalyzed reaction is much lower than for the catalyzed reaction. So again, technically correct, but that's not showing us that the overall amount of energy is the same. So our answer is this one. Very well done if you got that, because it's actually giving you correct statements, but it wants you to show that the overall energy doesn't change. Okay, the overall energy change doesn't change. So it's about that it starts at the same point and it finishes at the same point. Right, next one, 4.4. Copper is a catalyst in a reaction to produce ethanol from carbon dioxide. Ethanol, C2H5OH, is used as a fuel. Suggest why producing ethanol from carbon dioxide is sustainable. Now remember, if you get a suggest, you need to use your common sense. Okay, so you need to think about why that might be. So if we're using ethanol as a fuel, then we can say that the amount of carbon dioxide used to produce the ethanol because we can get that from plants. That's important. So if it's coming from plants, obviously it's taking in carbon dioxide as it's growing and then releases carbon dioxide when it's burnt. So if we've got about the amount of carbon dioxide to produce, that's 1 mark, is the same as the amount of carbon dioxide given off, then that's our 2nd mark. Okay, so we had to make that link that we can get ethanol from plants. As plants grow, they take in carbon dioxide, and that will be the same as the amount of carbon dioxide given off when you burn. We can say that they are carbon neutral. Right, and the last question for question 4. Chemistry plays an important role in sustainable development. What is sustainable development? And again, this is worth 2 marks, so we need to have 2 points in our question. So sustainable development means that you meet the needs of current generation okay, and that will get you 1 mark without compromising the needs of future generation. for a second mark. Or you could have said, but there's enough left for future generation. That also would have been fine. So total up the number of marks. This is out of 12, this question. And make a note of anything that you need to revise still, ready for any assessments. Okay, question 5. This question is about magnesium. A student investigated the rate of reaction between magnesium and hydrochloric acid, and we've got the apparatus that they used for that reaction. So you should be very familiar with the gas syringe, good accurate piece of equipment. We've got our hydrochloric acid, don't know how much. We've got our magnesium again, we don't know how much. Which is the correct ionic equation for the reaction? Now remember, if you see anything to do with ionic, it's going to be to do with charges because the electrons are transferred. So an ion is an atom or a molecule that has a charge. So if you ever see anything about ionic, think charges. So we've got a selection of different equations. So we need to think about what is losing and what is gaining electrons. So magnesium is in group 2, so it will lose 2 electrons and it will become a 2+ ion. Hydrogen, which is in the hydrochloric acid, that is going to be starting positive and then will make H2, the gas H2, which has no overall charge. So if we have a look at our different reactions, we can see that this one doesn't have anything about charges, so it's not going to be that one. This one says the magnesium starts off as a plus ion. It doesn't. Magnesium, when it's on its own before it starts the reaction, has no overall charge. So we are left with these two. Again, this one is saying that magnesium starts as a 2+, but it doesn't because it's magnesium plus hydrochloric acid, so that has no overall charge. So we're left with this one. So the magnesium, the hydrogen, which is positive, makes magnesium 2+ ions and H2. Okay, so writing ionic equations is quite a tricky thing. It is only in the higher. This one is a slightly nicer question because it's giving you options, so even if you are not sure, you can go through the process of elimination. 5.2. What happens in the reaction between magnesium and hydrochloric acid? Okay, so we've just gone through that is ionic. So we know that there is going to be something about the electrons moving and causing or creating ions. So electron sharing, that is covalent. So it's not that one, because if they're sharing electrons, care and share, covalent. Electron transfer, yes. Proton transfer, that can't happen. Okay, so protons cannot move from one to the other. So it is going to be electron transfer. Remember, as I said, anything to do with ionic is going to be transferring of electrons. And that's from paper 1 chemistry. So do be aware that they might ask you about that in this as well. Okay, 5.3. Table 2 shows the students' results. Plot the data from Table 2 on Figure 3. Draw a line of best fit. Please remember, in science, that a line of best fit can either be a straight line or a curve. And when we're talking about rates of reaction, 9 times out of 10 is going to be a curve. And that is going to be worth 1 of these 3 marks. So let's quickly pop in our points. So 0 is 0. Please remember to put your cross there. And please note that I'm using crosses. Don't use dots or hearts, because they will be looking at where the cross crosses over in the middle. That's where your point needs to be. Okay, so do use crosses. Use a nice sharp pencil. The next one is at 10 seconds. So here is 0, here is 20. So 10 is going to be halfway. and that goes up to 12.5. Remember, look at your scales. So that one, each little square is worth 4, and on this one, each little square is worth 1. So this would be 10, 11, 12.5. Okay, now don't worry if you've got little dots where you're trying to plot it out. That's absolutely fine. They're going to be looking at your crosses and then the line. Next one is at 35. So here is 30. So 35 will be halfway along that. And then that's going to go up to 36. So if you want to use a ruler, feel free. 30, 35, 36. Right, next one is 50. So again, we're halfway through the 40 and the 60, and that is going to go up to 43.5. So 41, 2, 3.5. Next one is 95 and 59. So here is 90. 95 will be halfway, and that goes up to 59. So that's 50. That's 60, so it must be here. So about halfway between that will be there. Next one, 120 and 60. So that's a nice easy one because we've got 120, and then that's going to go to 60. And then we've got 140 and 60 again. So once you've finished your graph, look at your points and look at which line is going to be best. So if I drew a straight line like that, then it's going to not take into consideration all of these crosses. So it is going to be a curve. And put your palm on the paper and use that as a pivot. So we need one single line going through the points, but it is not dot to dot, so don't do it as straight lines. And you kind of want to start curving up and then use the pivot to get your line. Okay, so 1 mark for the correct line, and you get 2 marks for the correct plotting of your points. You will have graph questions where you will have to draw a graph. This is a particularly hard one, so it won't get any harder than that. So very well done if you got that. Okay, 5.4. Describe, so you don't need to say why, you just need to describe the changes in the rate of this reaction. So you need to use the graph. What does this mean? This line is going up and then it is going flat at the top. And it's worth 3 marks. So we need to talk about 3 parts of this graph. So what we can decipher from this, I'll go back to the graph, sorry. We can split this kind of into 3. So you've got here, we've got it very, very fast, so there's a very steep gradient. So it's a very fast rate of reaction. Here it's starting to slow down. And here, where you've got the flat line, that means the reaction has stopped. So, describing, we can say that the rate of reaction decreases as it goes through. That would be worth a mark. Or I'd probably put rate of reaction fastest at start. So it begins off as a very fast rate of reaction, then it starts to slow down, so the rate decreases as time goes on. As time increases, that's going to be a 2nd mark, and then you can say the rate is 0 at the end, or the reaction stops at the end, so you can say from 120 seconds. Okay, you don't even need to put the number in because it's not asking you to use figures from the graph, but you can just say that it stops at the end or in the last 20 seconds. Right, so last part of question 5, explain. So now we need to say why. Explain why the rate of reaction changes. Give your answer in terms of collision theory. And again, it's worth 3 marks. So we've described it here, so we can just explain each part of this. So we can start off by saying that at the beginning, as it is, so there's more particles at the beginning, so more particles at start for reaction. And then as those bits of magnesium are reacting with the hydrochloric acid, it means that as time goes on, there's less of them. So the number of particles decreases during the reaction, or as time increases. And then at the end, why is it stopped? No particles, or no reactants would be even better word, no reactants left at the end. So that's why it stops. Okay, so this whole question is worth 11 marks. So tot up your number of marks and make a note of anything that you need to revise further. Okay, question number 6. This question is about oxygen and sulfur dioxide. Give the test and result for oxygen gas. So this is one of the gas tests that we need to know. So we need to say what the test is. That's where we're using the glowing splint. So that's the name of the test. And what happens to that glowing splint if it's in oxygen? It will relight, or words to that effect. So you get 1 mark for talking about glowing splint, and you get 1 mark for saying that it relights. Okay, question 6.2. This is a question about dynamic equilibriums. So the reaction between oxygen and sulfur dioxide is at equilibrium, so the rate of the forwards reaction, same as the backwards reaction. Some of the sulfur trioxide, so this one, some of that is removed. Explain what happens to the position of the equilibrium. It's worth 2 marks, and we have to explain, so we need to say why that happens. So you're going to get 1 mark for saying what happens, 2nd mark is going to be why that happens. So first off, if you're removing this, if that goes down, then the equilibrium is going to shift to the right. Okay, you're going to have more of this forwards reaction. Okay, so you can either say shifts to the right, or you can say about shifting for the forwards reaction, or favouring the forwards reaction. So I'm going to put shifts to the right. You can say favours the right hand side, any of those. Something about there being more of this reaction, and that's going to be 1 mark. Why does that happen? There's a couple of answers you could give. So you could say that because the concentration of SO3 has gone down. So it's going to want to produce more of it, which is why it goes for the forwards reaction. You could say that the pressure decreases, so instead of talking about the concentration, you can say that the pressure decreases on this side. Or you can say that it will want to produce more SO3 to re-establish equilibrium. Okay, any of those for your explanation for the 2nd mark. Okay, 6.3. Sulfur dioxide is an atmospheric pollutant. Sulfur dioxide pollution is reduced by reacting calcium oxide with sulfur dioxide to produce calcium sulfite. 7 grams of calcium oxides reacts with an excess of sulfur dioxide. It's giving you the relative atomic masses. A little clue, if it's giving you the relative atomic masses, you're normally going to have to find out some molecular masses in the question somewhere. Calculate the mass of calcium sulfite produced, and it's worth 4 marks. So if it's a 4 marker, there's going to be at least 2 stages that you have to undertake. So first off, we want to know, if I have 7 grams of that, how much of that is produced. So the first thing we need to do is find out the MR, the molecular masses of these 2 compounds. So calcium oxide is 1 calcium plus 1 oxygen, so that makes 56. And that's actually a mark. So even if all the rest of it, you don't get the maths correct, just working out the MR for these two gets you 2 marks. So we now need to find the MR of calcium sulfite, so CaSO3. So here we got 1 calcium, 1 sulfur and 3 oxygens. So if I pop that all into my calculator, that should give you 120, and that also is worth a mark. So we can say that 56 grams of calcium oxide will produce 120 grams of calcium sulfite, but we want to know how much it will be if 7 grams was used in the reaction. So we can do that by doing 7 divided by 56 and then multiply it by the 120. So that will also get you a mark, and that will give you 15 grams. Now there's a few mathematical ways in which you can do this, basically getting it into a ratio and then getting it down to 1, multiplying up. So if you got 15 grams, you automatically get the 4 marks. Okay, so there are other ways in which you can do that. You do get a mark for that and that, even if you don't get the 15 grams. So that is out of 8. Total it up and make a note of anything that you need to revise. Okay, so last question, question 7. This question is about hydrocarbons and crude oil. Hydrocarbon fuels are produced from crude oil, very exciting, but the question is asking you to describe how crude oil is separated into fractions, and it's going to be worth 4 marks. So again, we've got to make sure that we have 4 points at least that they can give us marks for. So you're basically going through the process. They haven't given you a picture on this one. You're going through the process of fractional distillation. So the first thing that happens to the crude oil is that it's heated up. Okay, you might have said that it is vaporized. Either one is going to get you 1 mark. That is the first step. We must make sure as well that we're talking about those 2 words that we kept talking about: evaporation and condensation. So you could have said that it's heated up to evaporate the crude oil or vaporize the crude oil. That also is a lovely answer. We then need to say about how the column is hotter at the bottom compared to the top. So you could say that the column cools as you go up. Okay, anything to the words to the effect that it is cooler at the top and hotter at the bottom will get you a mark. Then when it reaches the right temperature, it will then condense. So just having the word condense in there actually gets you a mark. And then the final point, that why is it condensing? Because it's at its boiling point. So I'm going to put depending on boiling point. So those are going to be 4 easy marks that you can get. Just make sure that you're including the science words and anything to do with fractional distillation. You've got to remember those words: evaporation and condensation. Okay, 7.2. Butane is a hydrocarbon. 2 equations for the combustion of butane are, and it gives you those 2 equations. You don't need to have known those equations. They have got them all balanced out. Why are different products formed? Now it's only worth 1 mark, so don't overcomplicate it. It's giving you the information here. So what is the difference between these 2 equations. You've got the same fuel coming in. We've got some carbon on the bottom one, whereas it's carbon dioxide on the top one. So that is complete combustion, and that is incomplete combustion. So why are the different products formed? We need to say about different amounts of oxygen. If you've said that the top one is complete combustion and the bottom one is incomplete, that also would get you that mark. Right, 7.3. One other product of the combustion of butane is carbon monoxide. Balance the equation. Now, before we get going on this, before I give you the answers, this is worth 1 mark. So if this is taking you longer than 1 minute, leave it and come back to it. Or if you think it's going to take longer than a minute, come back to it. This is quite a tricky one to balance. My tips for this are to put numbers underneath. So if you've got 4 carbons here, first thing you might want to balance is the carbons. So I'd say put your 4 down here, and then when you're happy with it, then put it into the spaces, because actually it's not going to end up as 4. The correct answer for this, if you go through the process, you need 2 of the butane, you need 9 oxygens, you need 8 carbon monoxides, and 10 waters. You are allowed multiples. So if you've put 4, 18, 16, 20, that would still get you the mark, just because this one is trickier. So our last question is about greenhouse gases. Right, so the last part of question 7, carbon dioxide is a greenhouse gas. Describe the greenhouse effect in terms of the interaction of short and long wavelength radiation with matter. Now that sounds like quite a complicated sentence, but actually it's really good that that sentence is in there, because it's reminding you to talk about the 2 different types of waves. So we've got 4 marks, so again we need to make sure that we've got at least 4 points in there. Remember, if you want to draw a picture to help you as you go through, please feel free. I'm not going to mark you down for that. So we've got our short waves coming in through the atmosphere, so that's going to be our first one. So short wave wavelength enters atmosphere. Like that, so always starting with a short, then that is absorbed by the Earth. Okay, then it's going to emit the longer wavelengths. So emits longer wavelengths. If you say emits infrared, that's absolutely fine. And then we need to say, because it's to do with the greenhouse effect, we need to say what happens to those longer wavelengths. So the longer wavelengths you can say trapped or absorbed by greenhouse gases. You could name a greenhouse gas instead of saying greenhouse gases, they still allow that. So you could say longer wavelengths absorbed, sorry, missed absorbed. So you should always check your answers. Absorbed by carbon dioxide, or you could say methane, that's absolutely fine. So longer wavelengths absorbed by greenhouse gases, so it doesn't escape. And that would get you all 4 of the marks for it. Okay, so this is very concise. Obviously you might have put it into sentences, but we need to talk about short wavelengths entering the atmosphere, passing through the atmosphere. We need to say about that it's being absorbed by the Earth, and we need to say that it's then emitted or re-emitted as infrared or as longer wavelengths, which are then trapped by the greenhouse gases. Okay, and that'll give you your 4 marks. So question 7 was out of 10, total up out of 10, and make a note of anything that you need to revise.